Steel can form car panels, yet also cut rock when hardened.
Hardness and ductility usually trade off, but steel can be engineered.
Today we follow steel from furnace to microstructure, step by step.
First, what hardness, ductility, and toughness actually mean.
Then, how heat treatment, quenching, and tempering tune those properties.
The secret is how carbon and crystal phases control dislocation motion. Hardness means resisting indentation and wear at the surface.
Ductility means plastic deformation, stretching without cracking.
Toughness means absorbing energy before fracture, especially under impact. Steel works because its microstructure can be changed, not just its shape. Inside steel, crystals deform through dislocations, tiny moving defects.
Carbon atoms pin dislocations, raising strength but risking brittleness.
So the question becomes, where is the carbon and in what phase?
Iron changes crystal structure with temperature, annealing transformations.
Heat treatment controls cooling paths to choose the final microstructure.
A perfect crystal would snap. Real metals bend because dislocations move.
A dislocation is like an extra half plane of atoms inside the lattice.
Under stress, dislocations glide, letting planes slip with less force. More dislocation motion usually means higher ductility.
Carbon sits in interstitial gaps, distorting the lattice around it. That distortion creates a pinning force, slowing dislocation movement.
Pinning raises yield strength and hardness, but can reduce ductility.
Alloying elements can also slow dislocations and stabilize phases.
Now meet ferrite, the room temperature iron phase, called BCC.
Ferrite is soft and ductile, and it dissolves very little carbon.
At high temperature, iron becomes austenite, the FCC phase. Austenite dissolves much more carbon, like a storage tank. Heat treatment first creates austenite, so carbon can redistribute. Then cooling decides whether carbon escapes into carbides or gets trapped.
Slow cooling lets carbon form cementite layers inside pearlite.
Faster cooling can produce bainite, a fine mixture with strong toughness. Very fast cooling forms martensite, trapping carbon in a strained lattice.
Martensite is extremely hard, but as quenched, it is often too brittle.
Tempering fixes that brittleness by relieving stress and forming fine carbides. Grain size matters. Smaller grains block cracks and raise strength. But overheating grows grains, lowering toughness and increasing brittleness.
So temperature and time are as important as the quench itself.
Microstructure is the software that runs inside the steel hardware.
Next, we switch from atoms to industry. How steel is actually made.
We start with ore, coke, and limestone, then turn them into liquid steel. We also track how impurities and inclusions can sabotage ductility.
Clean steel is tougher steel, even at the same hardness.
That is why secondary metallurgy is a critical step today. Now, let's go into the blast furnace and follow the chemistry. Steel starts with iron ore, or DRI, plus scrap steel for recycling. Coke provides heat and carbon. Limestone acts as a flux to form slag. The goal is to remove oxygen from ore and remove unwanted impurities. Key impurities include sulfur, phosphorus, and excess oxygen and nitrogen. Control begins with weighing charges and monitoring chemistry continuously. Even before melting, raw material quality affects final toughness. Moisture and rust raise hydrogen risk, which can cause cracking later. Now we enter the blast furnace, where iron making happens at scale. At the top, layers of ore, coke, and limestone are charged continuously. Hot air blasts in near the bottom. Coke burns, generating intense heat. Carbon reacts with oxygen to form CO and CO2, feeding reduction gases. Carbon monoxide rises and strips oxygen from iron oxides into metallic iron. Ft2O3 is reduced stepwise, ending as molten iron droplets at high heat. Limestone decomposes into CaO, which captures silica and forms basic slag. Slag floats, carrying oxides and impurities away from the iron below. Liquid iron collects at the hearth, often around 4% carbon. That high carbon makes it fluid, but it is not yet usable steel. Periodic tapping drains hot metal, followed by slag in separate streams. Operators watch temperature, composition, and slag behavior constantly. Too viscous slag traps impurities. Too thin slag can erode refractory. Refractory lining must survive chemical attack and thermal shock. The Ductile is violent. Heat shimmer, steam, and intense radiant energy. Hot metal is transported in torpedo cars or ladles to the next stage. Next is the BOF, where oxygen removes carbon fast and aggressively. Scrap is added first to absorb heat and prevent overheating. Then the oxygen lance descends, blowing pure oxygen onto the bath. Carbon oxidizes into CO gas, creating foaming and strong bath mixing. Silicon and manganese oxidize early. Phosphorus is captured by basic slag. Slag chemistry is tuned with lime to maximize impurity removal. After the blow, steel is tapped into a ladle, leaving slag behind.
During tapping, alloy additions can be made to hit the target grade.
Deoxidizers like aluminum reduce dissolved oxygen to prevent porosity. Templing checks carbon, manganese, phosphorus, and temperature in seconds. If carbon is too high, extra oxygen time is used. Too low needs recarburizing. Cleanliness matters. Inclusions act like crack starters under stress.
Modern plants use sensors, cameras, and models to control the blow precisely.
Some steel is made by EAF instead, especially with scrap and DRI feeds.
In EAF, graphite electrodes create arcs that melt scrap rapidly. Oxygen injection and slag foaming improve efficiency and impurity removal.
Once chemistry is close, steel is tapped to the ladle for final refining.
This ladle stage is where high-quality steel is really engineered.
Ladle furnaces reheat and stir steel to homogenize temperature and chemistry. Argon bubbling lifts inclusions upward and improves compositional uniformity. Vacuum degassing removes hydrogen and nitrogen, reducing embrittlement risk. Hydrogen can cause delayed cracking, especially in high-strength steels. Vacuum treatment lowers dissolved gases, so the steel becomes safer and tougher.
Desulfurization uses basic slag and stirring to pull sulfur into the slag.
Calcium treatment modifies inclusions, making them rounder and less harmful. Inclusion shape matters because sharp inclusions concentrate stress. Steel grades often require tight oxygen control for fatigue resistance. After refining, steel goes to continuous casting to become solid shapes. Liquid steel enters a water-cooled mold where a solid shell forms quickly. The strand is withdrawn while spray cooling continues solidification. Rollers support the strand to prevent bulging while the core is still liquid.
Secondary cooling zones precisely control temperature gradients and cracks.
The strand is cut into slabs, blooms, or billets using torches or shears.
Now hot rolling breaks down the cast structure and refines grain size.
Reheating brings slabs to rolling temperature for controlled deformation.
Rolling elongates grains, closes porosity, and improves toughness and strength.
Finally, controlled cooling can lock in targeted microstructures even before heat treatment.
Thermomechanical processing can produce strong, tough steel without quenching.
Cooling rate after rolling influences ferrite, pearlite, bainite, or mixed phases.
Microalloying with niobium or vanadium can refine grains and raise strength.
But for very high hardness, we still rely on quench and temper heat treatment. So now we move from the mill floor into the heat treatment shop.
Here, time, temperature, and cooling media become precise control knobs. We start by austenitizing, turning the structure into carbon-rich austenite. Then quenching creates martensite, and tempering restores useful toughness. Heat treatment begins by heating steel into the austenite region. This step dissolves pearlite and redistributes carbon into austenite. Temperature must be high enough for full austenitization, but not excessive.
Too high a temperature grows grains, reducing toughness after quenching.
Soak time must heat the core, not just the surface of thick parts. Uniform temperature is checked with thermocouples and controlled furnace zones. Atmosphere matters. Oxygen can scale the surface and remove carbon locally. Protective atmospheres reduce decarburization and keep chemistry consistent. Before quenching, parts may be preheated to reduce thermal shock risk. Fixtures must support parts to prevent distortion at high temperature. Now the steel is ready. Carbon-rich austenite, waiting for transformation. Cooling rate decides the path: pearlite, bainite, or martensite. Quenching forces a rapid drop to bypass diffusion-based transformations. That creates martensite, a strained structure with trapped carbon. Martensite delivers high hardness and strength, but also high internal stress. Gas-quenched martensite can be brittle, especially with sharp corners.
So tempering is not optional for most engineering parts.
Next, we compare quench media and the stresses they create. Quench severity ranges from brine fastest, then water, polymer, oil, and gas. Faster quenching raises hardness, but increases cracking and distortion risk.
Water cooling is uneven. Vapor film, then boiling, then convection stages.
That vapor blanket can insulate, causing unpredictable cooling spots. Agitation brings the vapor layer and makes cooling more uniform. Oil quenches more gently, reducing thermal shock for alloy steels. Polymer quenches can be tuned by concentration and temperature.
Gas quenching in vacuum furnaces can be uniform but needs alloy hardenability.
Hardenability means the ability to form martensite through thick sections.
Alloying elements slow diffusion, allowing martensite to form at lower cooling rates.
Thick parts cool slower in the core, so they may form mixed structures. That is why CCT curves guide engineers on cooling paths and transformation times. Quenching creates temperature gradients. Surface cools and contracts first. Meanwhile, the core is hot, resisting contraction, building tensile stress at the surface.
Martensite transformation also expands slightly, adding more stress complexity.
If stress exceeds fracture strength, a quench crack can form instantly.
Sharp corners concentrate stress, so radiating and smooth transitions are critical.
Distortion happens when cooling is uneven across geometry and thickness.
Fixtures and racking keep parts spaced for uniform fluid flow.
Quench tank temperature must be controlled. Warm media slows cooling.
Contamination changes cooling behavior, so quench oil is monitored and filtered. After quench, parts may be cold, but residual stresses remain locked inside. A quick hardness check confirms martensite formation at the surface.
But high hardness alone is not the goal. We need usable toughness. So we reheat for tempering, controlled and deliberate.
Tempering reduces brittleness by allowing carbon to form fine carbides.
It also relaxes dislocations and relieves quench stresses.
Now we explain tempering temperature as a property dial.
Tempering reheats steel below austenite temperature, then holds for time.
At low temperatures, hardness stays high, but toughness improves modestly.
At medium temper ranges, strength remains high, while ductility rises significantly.
At higher tempering, toughness increases further, but hardness drops more.
Tool steels may temper low to keep an edge. Springs temper higher for resilience. Time matters. Longer holds allow more carbide precipitation and stress relief. Double tempering improves stability and reduces retained austenite effects. Retained austenite can transform later under stress, changing dimensions. Tempering makes the microstructure, tempered martensite, strong and tough. Fine carbides act like tiny reinforcements while the matrix stays crack resistant. Impact toughness tests often show dramatic gains after tempering. Engineers select tempering by required hardness, impact energy, and fatigue life. Some alloys risk temper embrittlement in certain ranges and long holds. That risk is managed by composition control and proper cooling practices. For reduced distortion, martempering equalizes temperature before martensite forms. In martempering, parts quench to above M's, hold, then cool through transformation. Austempering holds in the bainite region to form bainite instead of martensite.
Bainite can offer excellent toughness with high strength and good ductility.
Case hardening treats surfaces differently, keeping a tough core beneath.
Carburizing adds carbon to the surface, then quench hardens the case. Nitriding diffuses nitrogen to create a hard surface without quenching.
Induction hardening heats only the surface rapidly before quenching.
These methods create hardware surfaces with ductile, tough interiors.
Now we connect heat treatment to the hard and ductile paradox.
Hard phases resist deformation, while tougher phases stop cracks from growing. This is why engineered microstructures outperform single-phase materials. Next, we summarize the full chain from ore to tempered martensite. And we map microstructures to real products like gears, bolts, and car steels. Now we can answer the main question with precision, not slogans.
Steel is hard, when microstructure blocks dislocations and resists indentation.
Steel stays ductile when the structure can deform without runaway cracking.
Quenching creates martensite for hardness, but it also creates brittleness.
Tempering converts brittle martensite into tempered martensite with toughness.
Hardness drops slightly, but usable ductility and impact resistance rise sharply.
Multi-phase steels combine hard islands with softer matrices to stop cracks. Grain refinement raises strength and toughness at the same time. Clean steel, with fewer inclusions and gases, behaves more ductile under stress. So hard and ductile is not magic, it is controlled structure and cleanliness. Let's map these ideas to real components you see every day.
Car body steels use phases that strengthen while still allowing forming.
Dual-phase steels mix soft ferrite with martensite for strength and ductility.
TRIP steels use retained austenite that transforms under strain for extra ductility.
Springs are quenched and tempered to flex millions of cycles without failure. Gears are often case-hardened, a hard surface with a tough core beneath. Bolts and shafts are quenched and tempered for strength with safety margin.
Knives temper to avoid chipping while keeping a hard cutting edge.
Structural beams rely on controlled rolling for toughness and weldability. In every case, the recipe matches the job's stress, wear, and impact demands.
So the full chain is chemistry control, cleanliness, shaping, then heat treatment.
If you want next, we can read TTT and CCT diagrams like a process engineer.
For now, remember, steel is programmable through microstructure. That is why one material can be both hard and ductile on demand. In slow cooling, pearlite forms as carbon diffuses into cementite lamellae.
Faster cooling limits diffusion, so structures become finer and generally stronger.
Bainite forms with controlled time temperature holds, often balancing strength and toughness. Martensite forms without diffusion. It is a shear transformation, fast and stress-producing.
Tempering lets carbon move short distances, creating fine carbides and relieving strain.
Testing confirms results: hardness, tensile strength, impact energy, and microstructure checks. Process control prevents defects: decarb, scale, quench cracks, and distortion. Geometry matters as much as metallurgy. Smooth radii reduce stress concentration. Clean ladle practices reduce inclusions that would otherwise trigger fatigue cracks. That is how steel becomes reliable, not just strong, in real machines. In slow cooling, pearlite forms as carbon diffuses into cementite lamellae. Faster cooling limits diffusion, so structures become finer and generally stronger. Bainite forms with controlled time temperature holds, often balancing strength and toughness. Martensite forms without diffusion. It is a shear transformation, fast and stress-producing.
Tempering lets carbon move short distances, creating fine carbides and relieving strain.
Testing confirms results: hardness, tensile strength, impact energy, and microstructure checks.
Process control prevents defects, decarb, scale, quench cracks, and distortion.
Geometry matters as much as metallurgy. Smooth radii reduce stress concentration. Clean ladle practices reduce inclusions that would otherwise trigger fatigue cracks. That is how steel becomes reliable, not just strong, in real machines.
In slow cooling, pearlite forms as carbon diffuses into cementite lamellae.
Faster cooling limits diffusion, so structures become finer and generally stronger. Bainite forms with controlled time temperature holds, often balancing strength and toughness. Martensite forms without diffusion. It is a shear transformation, fast and stress-producing.
Tempering lets carbon move short distances, creating fine carbides and relieving strain.
Testing confirms results: hardness, tensile strength, impact energy, and microstructure checks. Process control prevents defects: decarb, scale, quench cracks, and distortion.
Geometry matters as much as metallurgy. Smooth radii reduce stress concentration.
Clean ladle practices reduce inclusions that would otherwise trigger fatigue cracks. That is how steel becomes reliable, not just strong, in real machines. In slow cooling, pearlite forms as carbon diffuses into cementite lamella.
Faster cooling limits diffusion, so structures become finer and generally stronger.
Bainite forms with controlled time temperature holds, often balancing strength and toughness. Martensite forms without diffusion. It is a shear transformation, fast and stress-producing. Tempering lets carbon move short distances, creating fine carbides and relieving strain. Testing confirms results: hardness, tensile strength, impact energy, and microstructure checks. Process control prevents defects: decarb, scale, quench cracks, and distortion.
Geometry matters as much as metallurgy. Smooth radii reduce stress concentration.
Clean ladle practices reduce inclusions that would otherwise trigger fatigue cracks. That is how steel becomes reliable, not just strong, in real machines.
In slow cooling, pearlite forms as carbon diffuses into cementite lamellae.
Faster cooling limits diffusion, so structures become finer and generally stronger.
Bainite forms with controlled time temperature holds, often balancing strength and toughness.
Martensite forms without diffusion. It is a shear transformation, fast and stress-producing. Tempering lets carbon move short distances, creating fine carbides and relieving strain.